what I want to do in this video is introduce you to what I think is one of the neatest ideas in computer science, and that is recursion. So the way that we've defined this factorial function in the last few videos is actually an iterative definition. We are iterating through different values for this variable I, and then we're essentially taking those values, adding one, then multiplying those times our original product. And when we keep iterating through all of that, our eventual product has all of the values from 1 through the number multiplied by each other, and they're all sitting in this variable product. What I'm going to do here is rewrite this program. And what's cool about functions, I'm going to rewrite this function. What's cool about functions are, this function, we just say, look, it returns a factorial of a number. We don't care how this is actually written. And so anything that's using this function call, no matter how I implement it, as long as I implement it correctly, it shouldn't worry about it. So as long as I implement this, the insides, the guts of this function right, even if I could do it in a very different way, it shouldn't affect the behavior of any of the functions that call it. So let's go ahead and try to define this function recursively. And I think you're going to find this slightly fascinating. So I'm going to do it a little bit different. We're going to put some conditionals in here as well. So I'm going to say, so it's almost, in some ways, recursion is really deep and complicated. And on some levels, it's way simpler than anything else. So let me just put all of this stuff down there. So I'm going to say, look, if the number, you always want to think about a base case. What's a situation where if kind of the nugget or the smallest values we can put into for number that'll give us a decent response. So we'll say, look, if number is, let's say if it's less than or equal to 1. So if it's less than or equal to 1, let's just return. Well, then it's factorial. Let's just return 1, especially if we want to have the same behavior as the old function. The old function, regardless of whether we put a 1 there, a 0 there, actually even if we put a -1 or -2 there, it always gave us the factorial being equal to 1. So that's exactly what we're doing over here. We're returning 1 if the number is less than 1. And this also defines our base case. I can even label it here. So let me label. This is our base case. And you'll see what I mean for a second by a base case. And this is what I'm about to do now. This is the really exciting part about recursion. If the number is not less than or equal to 1, so I could write if. So this, or maybe I'll just write else, actually. So if the number is not less than or equal to 1, I'm going to return something different. And what I'm going to return is that number times the factorial of 1 less than that number. Now, the reason why this is fascinating and cool and all the rest is I just defined something using that something. So I just defined a function called factorial, and I define it using the definition of the function factorial. It is referring to itself. This is what recursive functions do. But if you think about it, and I'll diagram it out in more detail in the next video, so hopefully it makes a little bit more sense. It should kind of work. Because if you put a 1 or a 0 in for number, it'll just return 1. What happens if number is 2? Well, if number is 2, it'll say, look, number is not less than or 1, so I'll go over here. So it says it'll return 2 times factorial of 2 minus 1, or factorial of 1. And then it'll call factorial again, and factorial of 1 is just 1. So it'll return 2 times 1. So that'll work out for 2. Try it for 3. If you do factorial of 3, it'll go down to this clause over here, because 3 is not less than or equal to 1. It'll return 3 times the factorial of 3 minus 1, which is 2, the factorial of 2. Well, we know it already returns the right answer for the factorial of 2, so it'll return 3 times 2, which is 6, which is a factorial of 3. So hopefully you're getting the gist of it. Factorial of 4 is going to work for the exact same reason. It's going to boil down to 4 times the factorial of 3. We know that it works for the factorial of 3. And just to prove to you that I'm not doing some type of crazy voodoo and that this will actually work, let's try to run the program. Let's try to run the program right here. So let's try, this is some stuff that I was doing beforehand. Let me just get rid of that. So let's just run the program. So all I've done is I've redefined the factorial function, but I've redefined it recursively. So recursively, well, I won't have to change the comment. So let me save it, and let's interpret this program. Let's execute it and see if it does what we need it to do. All right. So they're prompting us for something. Let's take the factorial of 5. 120. And so once again, our factorial program, no matter what we put in there, it gives us the right answer. But what's really cool is it's now doing it recursively. When I do factorial of 6, saying, OK, factorial of 6. Is 6 less than or equal to 1? Well, no, it's not. So it goes to this else clause right over here. So then it says, return 6 times the factorial of 5. Then it says, OK, let me remember, 6 times the factorial of 5. Let's figure out what factorial of 5 is. Well, factorial of 5 is going to be 5 times the factorial of 4. And then that factorial of 4 is 4 times the factorial of 3, all the way down to the factorial of 1, which is 1. And so it'll actually return 6 times 5 times 4 times 3 times 2 times 1.